Let's now solve a few problems. The first problem is to show that in the punctured complex plane C minus 0, if you consider any closed curve, it can be homotoped to a closed curve whose image is contained in the unit circle. Let me write that down. Problem 1 is the following. Let omega be equal to C minus 0 and gamma from AB to omega be a closed curve. Prove that there exists a curve sigma such that a closed curve sigma such that gamma is homotopic as closed curves to sigma, and the image of sigma is contained in S1. S1, recall, is the unit circle, the set of all complex numbers z, so that absolute value of z is equal to 1. Let's give a solution to this. This is quite straightforward. We already start off with gamma, which is a closed curve in omega, and because omega is C minus 0, it means that gamma of t is not equal to 0 for every t in AB. So let's define sigma of t to be equal to gamma of t by the absolute value of gamma of t. And notice that because gamma of t is not equal to 0, this makes complete sense, and it's also a continuous function from AB into omega. In particular, if you look at the absolute value of sigma t for any t, that's going to be equal to 1. So this is indeed a curve which is contained in S1, and it's a simple check to see that sigma of A, this is equal to gamma of A by the absolute value of gamma of A. But gamma is a closed curve, and therefore this is equal to gamma of B by absolute value of gamma of B, which is equal to sigma of B. And therefore what do we have? We have that sigma is a closed curve with its image contained in S1. Of course, we have not proved anything about gamma being homotopic to sigma, but we will do that in a minute by explicitly defining what the homotopy is. We will in fact mimic the homotopy that was given when we proved that any two curves from a point z0 to z1 will be homotopic to each other if the curves are contained in if the domain is convex to begin with. Remember that there was a straight line homotopy, and that's exactly what we will be doing here as well. So define H from 0 1 cross AB into omega given by H of S comma t. This is equal to 1 minus S times gamma of t plus S times sigma of t. I'll in fact leave the entire process of checking that H is indeed a homotopy of closed curves from gamma to sigma as an exercise to you. Maybe I'll just check for you that H of S comma A, this is going to be equal to 1 minus S times gamma of A plus S times sigma of A. Then gamma of A is the same as gamma of B, and sigma of A is also the same as sigma of B. So this is going to be equal to 1 minus S times gamma of B plus S times sigma of B. We have already checked that sigma of A is the same as sigma of B. It's a closed curve, and this is precisely equal to H of S comma B. Therefore, at every stage S, H of S comma t or gamma subscript S t, that's going to be a closed curve at the point H of S comma I. So this is indeed a closed curve at every stage. and the fact that it is continuous is quite straightforward. H0 comma t will just turn out to be equal to gamma of t, and h of 1 comma t is just going to be equal to sigma of t. So I gave an entire proof of the fact that h is indeed a homotopy of gamma to sigma, homotopy as closed curves from gamma to sigma. And with this we conclude the problem. Let's now use the power of Cauchy's theorem to compute certain integrals which otherwise is difficult to compute. So let me write it down. Compute the indefinite integral 0 to infinity of cos of t square dt. At first glance, it might look like this has nothing to do with what we are doing, what we have been doing in this week, but let's see how Cauchy's theorem comes in to our rescue. It's actually quite magical the way we can use it. So notice that cos of t square is the real part of e to the power I t square, and therefore okay, before that 0 to infinity cos of t square dt, this is just limit as r goes to infinity of 0 to r cos of t square dt by the very definition. And cos of t square, as I have already noted, is just the real part of e to the power I t square. So we will focus on computing e to the power I t square dt. Let's now draw the complex in the complex plane what we are trying to do. We have 0 here and we have an r here, and if we look at gamma 1 of t to be equal to t for t in 0 comma capital R, then integral of e to the power I z square dz over gamma, this is just going to be equal to integral 0 to r e to the power I t square dt by a change of variable which we have discussed in the last week. So this is precisely what will manifest as integral of 0 to r of e to the power I t square dt. That means, let me draw in red the path along which we are computing the integral. But then our domain is, if you think of e to the power I z square, that's an entire function. It's holomorphic on the entire complex plane, and the entire complex plane is a convex set. And therefore, if you look at the integral of f from along gamma 0, which is a path from z0 to z1, and if we manage to get hold of gamma 1, another path from z0 to z1, then the integral of f over gamma 0 is the same as the integral f over gamma 1. And we are precisely going to do that. We will get an alternate path from 0 to r over which it's easy to compute this limit and approximate. And in order to do that, let's look at the following path, the path at an angle of pi by 4 and followed by the orange path, which is the unit, which is the portion of the unit, no, not unit circle, circle of radius r. So let me write the things down. This is say pi by 4, and suppose if you look at this as the direction, and suppose this is the direction of the second curve. So let me write them down. Let gamma 1 of t, this is gamma 1, and this is gamma 2. Oh, gamma 1 has already been taken, so let's call these things something else. Let's call this gamma 2, and let's call the third one as the gamma 2 of t equal to t times e to the power I pi by 4, where t is in the interval 0 to r. So if you notice, the starting point is the origin, it's a straight line in the direction of e to the power I pi by 4, and it ends at r into e to the power I pi by 4. This is exactly the point, r into e to the power I pi by 4. Okay, and how about gamma 3? Gamma 3 of t be equal to r e to the power I t for t in 0 to pi by 4. So if you notice, this is exactly the gamma 3 that we have described. Gamma 2 of 0 is this point, and gamma 2 of pi by 4 is going to be r e to the power I pi by 4. So yes, we have obtained the right parameterizations that we are interested in to compute integral of gamma 1. Let's see, integral of, so basically gamma 2 plus minus of gamma 3. Let's have a look at the image that we have drawn here. Gamma 2 plus minus of gamma 3 in the other direction. That is going to be the concatenation of these two curves is going to be a curve from 0 to r. And by Cauchy's theorem, on the domain complex plane itself, integral of f of z dz over gamma 1, this is equal to the integral of gamma 2 plus minus of gamma 3 f of z dz. And let's focus on integral of gamma 2 plus minus gamma 3 f of z dz. This is equal to integral over gamma 2 of f of z dz minus the integral over gamma 3 of f of z dz. This is precisely what we are going to get. And now let's use the parameterization to and the change of variable to say that this is equal to integral of what was gamma 2. Recall that gamma 2 was t times e to the power I pi by 4, and what was f of z? F of z was e to the power I z square. Let me just go up and show you what f was. F was e to the power I z square, and gamma 2 is t times e to the power I pi by 4. So this is going to be e to the power I times gamma of t, which is t e to the power I pi by 4 square, and gamma prime t dt. Gamma prime t is just e to the power I pi by 4 dt. So that's precisely what we will be getting from 0 to r. That is the first integral. And how about the second integral? The second integral is e to the power I z square. Now gamma 3, let's see what gamma 3 is. Gamma 3 is r e to the power I t for t in 0 to 2 pi. R e to the power I t square times r into I into the e to the power I t dt. That is precisely gamma prime t dt. So I am freely using whatever theory we have developed till now and writing the expressions down here. This is equal to integral from 0 to r e to the power will be minus 1, because I into I, e to the power I pi by 4 the whole square is e to the power I pi by 2. I'll just leave it to you to check that this is going to be e to the power minus t square, and e to the power I pi by 4 is going to be 1 plus I by root 2 dt. And how about the second term? This is just going to be 0 to pi by 4 e to the power I r square e to the power 2 I t into r I e to the power I t dt. Okay, now we are interested in the limit as r goes to infinity. So let's see what happens to each of these terms when r goes to infinity. Limit as r goes to infinity of 0 to r, or maybe I should write 1 plus I by root 2 times integral 0 to r e to the power minus of t square dt, which is going to be equal to 1 plus I by root 2 times 0 to infinity e to the power minus t square dt. Notice that e to the power minus t square dt is the standard Gaussian integral. In fact, minus infinity to infinity would have been the Gaussian integral, but we know from the Gaussian integral that this is equal to 1 plus I by root 2 times root pi by 2. That's precisely the limit as r goes to infinity of the first term. So this is something which has been taken care of. Now let's focus on the second term. The second term is the absolute value from 0 to pi by 4 e to the power I r square e to the power 2 I t. I think I am right here. I r square e to the power 2 I t, correct? R into I into e to the power I t dt. Limit as r goes to infinity. This is what we are interested in. Let's try to give, so notice that even though there are complex terms in the interior, in the integrand, the absolute value, if you look at the integral 0 to pi by 4 e to the power I r square 2 e to the power 2 I t into r I e to the power I t dt, even if we look at this particular integral, after writing it in terms of the real part and the imaginary part, we will be able to treat these as Riemann integrals of real valued functions on 0 to pi by 4. And from real analysis, we know that if you look at the absolute value of the integral of f of t dt, that's less than or equal to the integral of absolute value of f of t dt. This is all from a first question real analysis that we will be using. Using that, one can conclude that even for this Riemann integral, even though there are complex numbers involved, one can indeed compute. That's an exercise for you to conclude that this is less than or equal to e to the power I r square e to the power 2 I t into r I e to the power I t dt. This is something which we can conclude. And this is less than or equal to I into e to the power I t has absolute value 1. This is r times is less than or equal to 0 to pi by 4. We will just extract the absolute value here. Then we will be able to say what is this? This is equal to cos 2t plus I sin 2t. The cos 2t term will not contribute to the absolute value, it will just be modulus 1, and what will we have? We will have e to the power, the absolute value of e to the power, which is actually positive, minus of r square sin 2t dt. This is precisely what we will be able to conclude here. This in turn is less than or equal to, in the interval 0 to 2 pi, we can bound our function sin 2t as well, and we can say that this is less than or equal to r square t dt, which we will be able to say as being equal to r into r by minus of 1 by r square e to the power minus r square t evaluated from 0 to pi by 4, which is equal to 1 by r times 1 minus e to the power minus r square times pi by 4. Now, e to the power minus r square times pi by 4 is a number with between 0 and 1, and therefore this is in particular less than or equal to 1 by r. So what have we concluded? We have concluded that the absolute value here is less than or equal to 1 by r, and therefore the limit as r goes to infinity will be less than or equal to the limit as r goes to infinity here, and hence limit as r goes to infinity of integral over gamma 3 of e to the power z square dz is equal to 0. So the second term does not contribute. Let me go up and see. So this is going to be 0. So let's go up again and check what happened. This term vanishes. We have computed what this term is, and we have seen that this is equal to this particular term, the integral of f of z dz over gamma. So in particular, what we have computed is the following. We have proved that hence integral e to the power I z square dz over 0 to over gamma, or maybe 0 to infinity of this is equal to 1 plus I by root 2 times root pi by 2. Therefore, integral of cos t square dt from 0 to infinity, this is equal to root pi by 2 root 2. So is the case with integral 0 to infinity sin t square dt. So we have computed the integral. Let us do one more problem where we do such contour shifting to conclude something about certain integrals which might be otherwise difficult to handle. So problem 3, prove that the integral from minus infinity to infinity of e to the power minus of x plus I alpha the whole square dx, this is equal to integral from minus infinity to infinity e to the power minus of x square dx, which we know is equal to root of pi. So the point is to show that the integral on the left does not depend on alpha. Alright, let's prove it. So what is the left hand side? Minus infinity to infinity e to the power minus of x plus I alpha the whole square dx. This is what we would like to compute, and this is equal to the limit as r goes to infinity of integral from minus r to r e to the power minus of x plus I alpha the whole square dx. Let's again draw a picture on the complex plane as to what we would like to do. The green curve is where we would like to compute our integral over. So let's call this gamma 1, and let the red curve denote minus of r plus I alpha to r plus I alpha, the straight line joining minus of r plus I alpha to r plus I alpha. Let's call this gamma 3, and let's connect by using, say, pink these two and turn it into a rectangle, and let's call this gamma 2 and let's call this gamma 3. So let's now convert our real integral which is Riemann integral of real valued functions. Of course, there is an I featuring in here, but by looking at the real part and the imaginary part separately, this is just a real analysis problem. But let's convert it into a problem here by introducing the following. Consider the function f of z to be equal to e to the power minus of z square. Then if you look at e to the power minus z square, that is a function which is holomorphic in the entire complex plane. In particular, it's an entire function, and again, complex plane is a convex set, so we can apply Cauchy's theorem freely. Or in this case, we could apply Cauchy-Gursa, a special case of Cauchy-Gursa rather. Maybe you can connect the diagonal like this, consider this rectangle, this triangle and this triangle, and notice that the integral of the triangle, the first triangle, which is the sum of the integral over this straight line followed by this straight line followed by this straight line, and the integral of the second triangle, which is this straight line followed by this straight line and this straight line. When you add it up, the integral over this diagonal cancels off each other, and we get the integral over the bigger rectangle. And both the smaller triangles, the integral was 0, and therefore the integral over the rectangle will also be 0. Many times this integral over the rectangle being 0 is what is called the Cauchy-Gursa theorem. Now, if you parameterize these curves gamma, so let's see, gamma 1 of t is just equal to t, where t belongs to minus r comma r. Let's now look at what would be the integral of the function f of z over each of these curves. and try to see how we can relate it to our problem in hand. So integral of f of z dz over gamma 1, let's first explore that. That is going to be equal to integral of e to the power minus z square. This is going to be e to the power minus t square dt from minus r to r. This is precisely what integral over gamma 1 is going to be. If you notice, that is the thing written to the limit as r goes to infinity is what is written to the right here. Integral over gamma 2 f of z dz. Okay, what is gamma 2? Gamma 2 of t, that's the straight line path which connects r to r plus I alpha. So this is just going to be equal to r plus I t, where t belongs to 0 comma alpha. So this will be equal to f of z is e to the power minus z square, and that's going to be e to the power minus of r plus I t the whole square, which is going to be r square minus t square plus 2i r t, and then gamma prime t is just going to be equal to I dt. This is what we will be getting for gamma 2. So if you now take the absolute value, that's going to be equal to the absolute value here, and by a very similar argument as given earlier, this is just Riemann integral of the imaginary part and the real part, and that by using theorem from the first course on real analysis is going to be less than or equal to 0 to alpha, the absolute value of whatever is inside, which is going to be e to the power minus r square minus t square dt. Notice that t square is going to be less than or equal to alpha square. So notice again that alpha is not necessarily a positive number. Alpha, oh, I didn't write that in the problem. For all alpha in R, we have not put any restriction on alpha being just a positive number. Alpha could be any real number. This is true. So the figure that we have drawn might not be representative. It could have been the case that the gamma 3 is in the lower half plane rather than in the upper half plane. However, whatever conclusion is being drawn here, that's going to be right. So if alpha is actually a negative number, the curve gamma 2 would be r plus it, where t is from alpha to 0 because alpha is a negative number. So we would still have similar equality here, except that the integral will be from alpha to 0 here instead of 0 to alpha, but for the sake of absolute value, it shouldn't matter. And because t belongs to either 0 alpha or alpha comma 0, t square is certainly going to be less than alpha square. And because of that, this is less than or equal to 0 to alpha for all t in 0 alpha in this case, and if alpha is negative, it's alpha 0. This is less than or equal to e to the power minus of r square minus alpha square dt, which is less than or equal to alpha e to the power alpha square by e to the power r square, and if you take the limit as r goes to 0, this goes to 0 as r converges to infinity. So the integral of f over gamma 2, that is converging to 0 as r goes to 0. Similarly, the integral over, this was gamma 2, this was gamma 2. Similarly, integral over gamma 3 is also going to be 0. A very similar computation will tell us that. Integral f of z dz over gamma 3, not gamma 3, gamma 4 converges to 0 as r goes to infinity. So let's now only worry about, we have taken care of gamma 1, we have taken care of gamma 2, we have also taken care of gamma 1, gamma 2 and gamma 4. So this should have been 4. We have taken care of this as well. Let's now worry about gamma 3. What is the integral of f of z dz over gamma 3? What is gamma 3? We would rather conclude the result over minus of gamma 3. Gamma 3 would be in this direction. Let's see what minus of gamma 3 is. The reversal. We'll try to find out what this is. Let minus of gamma 3 of t, this is a map from minus of r plus I alpha to r plus I alpha. So let's define it to be t plus I alpha, where t belongs to minus r comma r. And by substituting it, e to the power minus z square, that's what we are interested in. This is going to be equal to integral e to the power minus of t plus I alpha the whole square dt from minus r to r. And if we take limit as r goes to infinity of integral over minus gamma 3 of f of z dz, that's precisely equal to integral minus infinity to infinity e to the power minus of, let me just do a change of variables here and write it as dx. Okay, now let's go up and apply Cauchy's theorem or Cauchy-Gursa to this particular setup. By Gursa's theorem or Cauchy-Gursa's theorem, we have integral of f over gamma 1 plus integral of f over gamma 2 plus integral of f over gamma 3 plus integral of f over gamma 4 is equal to 0. And as r goes to infinity, this vanishes and this vanishes. And therefore, we have integral of gamma 1 plus integral of gamma 3 is equal to 0. By Cauchy-Gursa, we have integral of f of z dz over gamma 1 plus integral f of z dz over gamma 3 is equal to 0 as r goes to infinity. And therefore, integral of f of z dz over gamma 1 is equal to minus of integral of f of z dz over gamma 3, which is the same as integral over minus gamma 3, the reversal of f of z dz, and we have explicitly computed both these numbers, both these quantities. The right hand side is going to be e to the power integral of e to the power minus of x plus I alpha the whole square dx from minus infinity to infinity. And this is going to be integral e to the power minus of x square dx from minus infinity to infinity. And that's precisely what we had set out to do. In the next problem, we will address the question of existence of an inverse to the exponential function. Classically, this is what is called as the logarithm in real analysis, but we have not defined an analog of the logarithm for complex numbers. So, in this problem, we will be addressing one such question. Problem 4. Let omega be a simply connected domain Recall that a domain is simply connected if for every closed curve at a point z0 is null homotopic to the constant curve at z0. Suppose omega is a simply connected domain and f be a map, holomorphic map on omega into C minus 0 such that f of z is not equal to 0. And let's put one more condition that f prime is also holomorphic. So I would like to mention at this point that this is a redundant condition which we will be proving very shortly. If f is holomorphic, we will be able to show that f prime is also holomorphic. So I didn't have to put this condition into the hypothesis of this problem, but as of now we have not proved that f is holomorphic implies f prime is holomorphic. So let me just put that into the hypothesis here. So this is for all z in omega. Okay. Then there exists g from omega into C such that f of z is equal to the exponential of g of z. Notice that if omega is such a domain which does not contain the origin, it's a simply connected domain which does not contain the origin, and if we consider the identity map f of z is equal to z, then in particular that is a holomorphic function, and the conclusion tells us that we will be able to get hold of a function g which will behave like the logarithm such that exponential of g of z is equal to z. So, this is in some sense the extension of the classical logarithm which is defined on the positive real numbers. Let us give a proof of this. The proof is quite straightforward. Now that we have the tool of Cauchy's theorem at our disposal, this can be proved quite easily. Consider the function f prime of z by f of z. Notice that f of z does not vanish in omega. For every z in omega, f of z is not equal to 0. So, 1 by f of z is a holomorphic function, or in particular f prime by f of z is a holomorphic function, is holomorphic on omega. What do we know about omega? And by applying Cauchy's theorem to simply connected domains, we can say that every holomorphic function defined on a simply connected domain has an antiderivative. So, since omega is simply connected, there exists an antiderivative g of z such that g prime of z is equal to f prime of z by f of z. Now, let us consider the function g. G is basically, or rather let us define h of z to be equal to the exponential of g of z. We know that g is a holomorphic function. We also know that exponential is a holomorphic function. Composition of holomorphic functions is going to be a holomorphic function, and we also know that exponential does not vanish. Therefore, h is a function which does not vanish on omega and is holomorphic on omega. Let us consider f by h and look at its derivative. The derivative by quotient rule is going to be equal to f prime times h minus f times h prime by h square. And if you notice, f prime times h minus f times h prime, this is going to be equal to f prime times what is h? H is going to be exponential of g of z minus f times the exponential of g of z times g prime of z, and g prime of z is going to be f prime by f. The f's will cancel off here and we get that this is equal to 0. This is the case on omega. Therefore, we have f prime, or rather f by h prime, this function is 0 on omega. That means by elementary calculus we can conclude that f is equal to a constant times h. Now that means that i.e. f of z is equal to c times the exponential of g of z. Let c prime be some number such that e to the power c prime is equal to c, then we have f of z is equal to the exponential of g of z plus c prime. That is precisely, so we will call this new function as g, and that is precisely what we were trying to find out. We have a function g such that exponential of g, in this case, let me in that case do one thing, call this g0, just change the notation above as well. Let g0 be this function, alright. So, this define g of z to be equal to g0 of z plus c prime, and that is the function we were looking for. Let me stop here.